Hey, welcome back. So we would really like a formula, a mathematical formula, to predict the amount by which the boiling point goes up and the freezing point goes down. And it turns out that we can certainly do that. And in the last example, we looked at water, and we noticed that the boiling point increased by 0.512 degrees every time the concentration went up by 1 mole per kilogram, or 1 MOLAL. So we can go ahead and we can write a formula here. We can say the change in boiling point is equal to the MOLAL concentration, I'll write that M, times by essentially the slope of that graph, which was 0.512 degrees C per MOLAL. So we can go ahead and we can write it like that. So remember, M here is our MOLAL concentration. It is the total concentration in moles per kilogram of solute, and this 0.512 here is just essentially the slope of that line. We notice the same thing for the freezing point as well. So for water, there was a depression that was related to the concentration. So I can write the MOLAL concentration, and the slope of that graph was 1.86 degrees C every time the concentration changed by 1 mole per kilogram. And so we can write this equation here. In fact, this is for water, but water is not the only solvent in the world. So in general, for any solvent, we can write a more general equation that looks something like this. We can say the boiling point of the solvent will go up. It's proportional to the concentration of the solute dissolved in it, times by a factor. And we're going to call this factor Kb, and we're going to call this the boiling point elevation constant. So this is the boiling point elevation constant. And for every solvent, there's a different value. So I'll go ahead and show you a table here in a minute. But for water, we can see above it's 0.512. But for something like benzene, it'll be completely different. The freezing point also goes down using the same kind of equation here. And so the proportionality constant, which is just the slope of the graph of temperature versus concentration, we call Kf. And that is the freezing point depression constant. And again, we always have to remember, right, the freezing point's going down, and every solvent has a particular value. So we can go ahead and we can look that up in a table, and we can use it to calculate any kind of boiling point or freezing point we can if we know the solute and, or rather the solvent and the solute concentration. So this is a table right out of our textbook, and it lists 6 common solvents, their regular freezing point and boiling points, and the freezing point depression constants and the boiling point elevation constants. So remember, the freezing points go down, the boiling points go up. So let's go ahead and take some benzene, right? And maybe we want to know, what's the freezing point of benzene? Okay, well, I mean, if that's all it was, right, we could just look up the table and we could say, well, benzene is right here and it freezes at 5.5 degrees C. But we're going to dissolve something in it. So what's the freezing point of benzene with 1.7 moles per kilogram of formaldehyde dissolved in it? Okay, so we got a solution now. So what do we have here? We've got the normal freezing point of benzene. So the normal freezing point of benzene is 5.5 degrees C. And we've got to remember the equation here. So delta TF is equal to Kf times by M, or M times by Kf, however you want to do it. We look at the freezing point constant for benzene, and it is 5.12 degrees C per molal. And then we multiply by the M here. M here is the MOLAL concentration. And I think this is kind of naughty, actually, because we're using M for both the units, moles per kilogram, and for the symbol itself for MOLAL concentration. So it's kind of sloppy, but there you go. All right, what was the MOLAL concentration? We said it was 1.7 moles per kilogram in the problem. And now you can see the reason for those units. So the units for those freezing point constants are designed in a way that when you multiply them together, you get the units of degrees C, and the concentration units cancel out. So I get 8.704 degrees C. In terms of how well we really know that number, well, the concentration was only good to 2 significant figures, so when we multiply, we probably don't know past this second digit here. All right, now we got to calculate the freezing point. So what happens here is the freezing point goes down, so the new freezing point is the old freezing point, right? The original freezing point of the pure thing minus the freezing point depression. So you don't have to write it as an equation if you want to. You just have to remember that the freezing point is going down by whatever you calculate here. So what do we have? We got the 5.5 degrees that we start with, and it's going down by 8.704 degrees. And again, we're doing a subtraction, so we really only go by the digits after the decimal point. So that is going to be minus 3.2 degrees C. And just to maybe double check that we've, paid attention to the rules here of dealing with numbers, maybe we can write 1 point dp next to it. So 1 decimal place, that means. And just for fun, right, we can do one more problem. We can say, what's the boiling point what's a good one here? What's the boiling point of carbon tetrachloride, which has, what should we have in it? Let's go ahead and dissolve some formaldehyde in it at a total concentration of, say, 3.8 moles per kilogram. In fact, maybe that's one you can try. So what's the boiling point of carbon tetrachloride that you've dissolved formaldehyde in, so you've got a total concentration of 3.8 molal. So pause the video and have a go, and then we'll compare notes. All right, so if you're back, so let's see if we got the same number. So we can write the boiling point elevation constant, right, or equation is equal to the boiling point elevation constant times by the molal concentration. What are we dealing with here? We're dealing with carbon tetrachloride, so it has a normal boiling point here and a boiling point constant of 5.03. And those have units of degrees C per molal. The concentration we had was 3.8 molal. So when we multiply together, the molal cancel out and we get degrees C. And my calculator says 19 and a bit, so 19.1. I really shouldn't go past that 9 there because I only have 2 significant figures. That's not the boiling point, remember, right? That's the boiling point elevation. So the actual boiling point itself is equal to the original boiling point, which was 76.7 degrees, plus, right, because we're elevating it 19.1 degrees. And if we calculate that, we get 95.8 degrees C, and actually you can probably argue that we should have no decimal places, so that is 96 degrees C. So pretty impressive, huh?